Good morning, everyone. Daniel Vetter here giving the next talk on Intel graphics, I think. Yeah, GPU drivers. And if there's any questions, if we could hold them till the end of the talk, and then I'll bring you a microphone and ask your question into the microphone. Good. Please welcome.
So yeah, welcome. Thanks for coming. I'm going to talk about GPU. I work for Intel in the open source GPU driver team. But the talk is about GPU drivers in general, open source GPU drivers in general. And how great things are. Because, so the reason for this talk is 10 years or so ago, the state of open source graphics driver was not so great. I mean, we had a few things, like we just merged the graphics execution manager, which was kind of finally a real kind of memory and execution manager for GPUs a few years after Windows, quite a few years after Windows. So you could actually run 2 GLX Windows at the same time, and your desktop could do wobbly Windows. Absolutely awesome. We just merged kernel mode setting, so the first glance of hope for a somewhat modern display interface. But that was about the extent of kind of the good news. If you looked at drivers, there was essentially the Intel driver, the i9-15 driver, and there was a Radeon driver. And nothing else really with this new modern graphics memory manager, the new modern the kernel interface for display drivers. We had this entire thing with this new kernel mode setting was just for the Linux desktop, and all the embedded people were using the FBDEF interface with a big chunk of driver. Like, why did we have to take a small community of people doing open graphics driver and cut it in half? We were proudly celebrating achieving OpenGL 2, while OpenGL was definitely getting irrelevant compared to DirectX. And of course, we were a few years late. So just an all-around general wasteland. And if we compare this to today, on the kernel side, graphics has become the second largest subsystem, like 15% of the kernel, plus an equally big chunk of code with lots and lots of people working on it on the user space side. We have now 57 atomic Modeset drivers, which is already like the next fancy version of the kernel mode setting interface. And more others, like sub-drivers, component drivers, and some of the old ones that haven't been converted. And the cool thing is, I gave a somewhat similar talk in autumn in Lyon, in Europe, and I had to actually adjust the number and increase it by 3 in like just 3 months. We have latest OpenGL. We have latest OpenGL ES for the kind of embedded applications. We have Vulkan, which means we finally have an open graphics standard again that's relevant. If you look at the drivers, at the Modeset drivers, just the smallest drivers we have, and this is a full functional driver, is just 250 lines, whereas the biggest, the one for AMD GPUs, is over 2 million lines. So we scale, at least by code size, by like 4 orders of magnitude. So if you compare kind of 10 years ago and today, this is a tremendous success story. And I want to explain a bit like the technical stuff, how we got there, what it took, and what I think are the lessons learned we could perhaps take away from this. So first, let's look at some of the technologies we managed to create over the last 10 years. And one of the really awesome things that I think really worked out great is the new atomic Modeset API. So remember, like 10 years ago, we merged kernel Modesetting, first promise, but it was just focused on the desktop, a fairly simple use case. You just light up the display and it's done. And you'd think, how hard can it be to just light up the display and it's done? So the thing is, if you look at embedded applications with power management and power usage and power efficiency matters hugely, they have lots of special hardware scan-outs planes for like videos and doing videos in your browser window and kind of rendering a lot more with hardware on the desktop, or we have multi-screen and it actually works. Mostly, if the driver is correct. And the thing is, as soon as you go from one screen to 2, 4, 3, 4, like the hardware engineers like to save a bit of costs and share stuff. So suddenly you can light up 3 screens, but only if 2 of them use the same refresh rate. And all these kind of things. We have a lot more features for like color space conversions. There's cool stuff where you do write back, so you use the display hardware to composite your desktop, and then when nothing changes, you write that back in kind of compressed version, so you use less memory bandwidth and save again a bit of power. VGA is kind of dead. And if you compare this to DisplayPort, you have like an entire network with a protocol, and the other thing can randomly disappear or have failures. We haven't have content protection and made a bit news about supporting that, and everything else. And so essentially what we've done with Atomic Modeset is allow us to do all that and create a new user space API so you could do a display change in one go. So instead of lots of flickering and then everything rearranges and lots of tearing, you can just give the kernel, here's the new thing I would like to do. Please do it, and the kernel says, yes, this works. Oh, sorry, it doesn't work, like I've run out of clocks and stuff like that. And this is kind of the new modern display driver hardware. And like I said, we have like almost 60 of these drivers now supporting all kinds of things. And you think like, for something that's this powerful, writing a driver for it must be an endeavor. But here's a little case study for a tiny embedded display controller. I think it's for one of these little LED displays that you might want to use in an embedded application with just like displaying a few lines of text at most. And it supports everything. So it supports full Atomic, the latest and greatest user space API. And on the top of that, we have the legacy compatibility layers. So the old kernel Modesetting is supported, FBDEF is supported. And the way we get to like almost no lines of code is we have this defm, which is device managed allocations and ref counting in the kernel. So essentially you just initialize everything, and when you hot unplug your little display from the board and disappears, like none of the driver code actually has to clean up anything. That else happens automatically. It's a kind of garbage collecting. We have DMA buff. This is for buffer sharing. I'm going to cover this later on. So you can actually have like on your SoC a real GPU that renders stuff and then display it on your little panel. The only thing that's missing is suspend resume. I'm not sure why it's not wired up. That would be like 2 functions, including white space, 10 lines of code. Anyway, this is 250 lines of code. And the other example of an atomic driver was the AMD GPU driver with a completely new display stack written for Linux. But unfortunately, they didn't talk to us first. So they shoveled an entire OS abstraction layer in there. And it took us about 2 years of occasionally newsworthy discussions on the mailing list, explaining how you could write a full-featured driver without this abstraction layer, which we really didn't want, it's just getting in the way. I mean, the point of free software is you can change it. And if they shovel this abstraction layer in there that's only relevant for other operating systems, you can't really change it. Anyway, we managed to merge it. And kind of between these two drivers, the lessons learned from Atomic is Atomic is a transactional API, like a database. But it doesn't work like a database. You don't do a try and a rollback, because if you just try and change the harvest state, you still have to flicker, and users would still be disappointed. So what we actually do is we present the entire update of the harvest state, check it, and we do that with freestanding state structures. So if anything goes wrong, if any constraint is violated, we can just release the memory and nothing bad has happened. And only once everything is validated, we commit it to hardware. So it's Atomic, but not kind of the usual try rollback. And then the magic of scaling for orders of magnitude in driver source code size, we achieved that with helper libraries. So the driver gets the full power of Atomic interface, but then you can, with few lines of code, add helper libraries that kind of simplify it or give you support for specific hardware features. And the only thing that's really done in the core is the kernel user space marshalling. So we shovel quite an impressive data structure between user space and the kernel. And it's essentially serialized. And the deserializing is done in the kernel. And the locking, experience says no one understands locking, me included, so we try to just write that once. And the one thing that's still missing is we definitely need better test cases and proper UAPI specs. We have a really nice documentation for kernel drivers, and people are happy with when they need to write a kernel driver for it. But essentially, the people who want to write compositors using full Atomic, they're a bit lost. Here's two references. I mean, obviously going to upload the slides if you want to learn more about this great thing, because it really solves everything while keeping things simple at the same time. And that was quite a challenge to achieve. So the next technical topic I want to look at is one that spans the full stack. So 10 years ago, like, you had the GPU, and that was the one GPU you had. But since then, in laptops, you have multiple GPUs. The integrated one, that's really power efficient, but kind of crawling slow. And the more powerful one, or maybe you have a desktop with multiple GPUs. Or especially on SoCs in the embedded world, like you have a 3D render core from maybe ARM Mali, and the display core from your SoC vendor, and then maybe a third thing that does video transcode. And you need to make these things talk with each another. And the thing is, if you have a GPU pixel buffer, this thing is not simple. Usually you think you just have an array with like one line after the other of the pixels. And that's extremely inefficient for rendering. So all the GPUs rearrange the pixels into tiles and move them around, so that when you draw like a horizontal line, you don't jump like a few hundred kilobytes between each lines and totally piss off your memory controller. But they're all different. So you need to agree on this. And the way we solve this is with these so-called DRM modifiers. You don't just need to agree on the pixel format, like 24 bits or RGB or 30-bit RGB, but you need to agree on the exact like placement and rearrangement of the individual pixels, and sometimes the bit encoding. And what's even more important, especially in embedded, frame buffers get compressed. So you have like a data plane and a bunch of compression metadata. And obviously you need to agree on the exact compression mode. and that saves a lot of memory bandwidth, and memory bandwidth generally means less power consumption. And we now have Vulkan extensions for this, OpenGL extensions, Wayland and X11 protocol extensions. Even NVIDIA supports this now, which is awesome. What still needs to be done is, if you do this compression, and especially with the compression stuff, it might be that your client application has already decompressed it. And then your compositor gets it and says, this is compressed, but oops, I need to decompress it. And so you decompress twice, which is not great. So these dynamics changes and compression states and all these things, there's also really strange stuff like you can do a really optimized format if you line up one plane, and as soon as you one display, and as soon as you plug in a second one, the hardware needs to be reconfigured, and that special superpower optimized mode doesn't work anymore. So you need to tell all your client applications, please render in the other thing, because I can't display the first one and you don't want to do a copy reframe. So we solved this with modifiers, but the other thing is, even if everyone agrees on the bit precise data format, you still need to make sure that the next chip or the display or the next processing thing in your pipeline, from like maybe video decompression to post-processing to display, doesn't start reading before the first one has finished writing. So this buffer sharing cooperation also needs synchronization. And 10 years ago, we had nothing. It was just tearing, and everyone was disappointed. So the first attempt was implicit synchronization. So you passed buffers around, and user space was ignorant. And the kernel tracked when someone was writing something and when someone was reading something, and tried to make sure that the second driver wouldn't start with the processing before the first one was finished. Magic behind the scenes. We spent, I think, 1-2 years doing lots of refactoring for common infrastructures to extract so-called DMA fences, which are an ongoing GPU operation, and DMA reservation object, which kind of tie them together so you can track readers and writers. Unfortunately, people figured this is not enough rope for user space to hang itself. They want to manage synchronization themselves so that they could do split buffers and like render here and read here and then flip around in the same buffer. And the kernel tracking just one kind of access rights per buffer was too coarse. So this was mostly demanded by Android. We pulled that out, made it using the Android infrastructure that was kind of existing already out of tree, added an explicit user space API so that user space could handle these synchronization points and tell them the kernel, which was great, except every frame you had to handle these DMA fence objects around. So like I rendered this, I got a fence for it, and now you give it to the next one, here's the fence. This is not fast enough, so the people from Vulkan who really care about low overhead and speed, they created a new synchronization primitive. In Vulkan, it's called a timeline, a sync object, I think. And we created DRM sync objects, which is essentially just a fancy container for these synchronization thingies, the fences. So instead of always having to pass things around, you do like buffer sharing. You share it once, kind of the synchronization primitive, and then one side just shovels stuff in and the other just pulls it out, and it works without the two people, the two parts having to talk with each other. That was still not good enough because you still had the need for multiple of these sync objects. So the thing that's currently happening is Vulkan is extending these sync objects to entire timelines. So one guy could say, okay, I'm just going to process the even ones, and you take the odd ones, and we have this rule of protocol, and then we never talk with each other and just get stuff done. So we're roughly at version number 5 in this thing. And as the dots indicate, we already know it's not good enough. So what a lot of people would like to do is kind of like mutex is fast user space mutex locks, but they would like for at least a fast path to do all this synchronization between user space running on the CPU and the GPU without ever getting the kernel or anything else involved. So yeah, there's turns out buffer sharing and making sure there's no tearing and corruption and everyone agrees is quite a tough problem, but we're getting there. Then another area of the graphics stack is obviously user space, like for OpenGL. All the fun stuff happens in the user space, and the only thing the kernel really does is make sure that user space can't break out of the box and do a bit of security boundary breakage. So that's why we have the graphics execution memory manager in the kernel. Keep that all separate. And the challenge in user space, or one of the really big challenges, you need a compiler. You have these fancy programmable shader cores on your GPU that can do all kinds of funny stuff. And you have lots of different standards and kind of graphics-specific languages for programming these. And we had quite an evolution of compilers. So the first shader core languages were very simple. Essentially, you just gave something that roughly resembles bytecode to your driver, and it was more or less a one-to-one translation to what the hardware was executing. But that changed pretty quickly, and hardware people added stuff like control flow and loops and all these things. And shaders become ever more complex. They were not just blending a few textures together and done. There's all kind of these materials that, depending upon lighting, try to do the right thing. And then people started to figure out that GPUs are really good at number crunching, and started writing entire simulations in kind of the general purpose compute stuff. So you need a real compiler. That thing needs to optimize it. And the first thing we had was the Mesa. Mesa is the 3D API. IR, which really was just the bytecode with a bit of compiler stuff smashed on top. Not really an intermediate representation you could do anything useful with. Really terrible. So, but it was good enough for the hardware like 20 years ago, or 15 years ago. The next evolution is TGSI, which tried to standardize a bit more, because you had like multiple APIs on the application side, like OpenGL, OpenGL ES. Maybe you wanted to do video transcode and stuff. So you needed to have some standard, and drivers needed to interpret that. It was kind of on the same level as Mesa IR, but with no optimization support, just as an intermediate representation to glue the bits together. And then the OpenGL 2 thing happened, and people realized pretty quickly this actually needs a real compiler for OpenGL 2 that added GLSL, the GL shader language, which is something like C, or it looks like something like C. And the first simplistic compiler was thrown out. We got a new one with its entire intermediate representation, and lots of work put into it for optimization passes. Another group of people figured, well, writing a compiler that actually does something useful is hard, so let's pick an existing one, and they went with LLVM as kind of the intermediate representation for all the optimization. Plus, every driver had like 2-3 compiler backends that took the optimized intermediate representation and tried to do something useful with this. And it turns out like GLSL IR was too much looking like a Alexa parser thing, and not like something you could actually optimize. So For those who know a bit about compilers, it did not have an idea about SSA, so single static assignment, I think it's called, which is since, I think, 2-3 decades, the way you do most of the optimization passes. LLVM is really great for CPUs. Unfortunately, GPUs do not work like CPUs. They have a very opinionated idea about how control form is supposed to look like. And the LLVM people are not interested about this. And if you kind of throw this information away about control flow and then try to rebuild it, you're just playing a losing game. So the really great thing that happened over the past few years is that NIR was created, which stands for New IR. Absolute great name. And the thing is, this is finally kind of the GPU compiler infrastructure to really unify and rule them all. It's replacing LLVM in the AMD compiler. It's replacing all the optimization passes in the old GLSLIR compiler. And all the new drivers that are getting built in open source through reverse engineering, they're all based on the NIR infrastructure. And I myself, I have like absolutely no idea about compilers. But just last year at our yearly conference, there was a great talk by Jason Ekstrand about how not to write a compiler backend, kind of summarizing 10 years of learned lessons about writing GPU compilers. And I mean, this is just one aspect of all the awesome drivers we have nowadays on the user space side. For embedded SoCs, we have one for Panthros, which is for the new ARM Mollies. We have the Lima drivers, which is for the really old ARM Mollies. We have the Freedreno driver, which is for Qualcomm. Pardon. Etnaviv, which is for Vivante hardware, which is some really small embedded chips. The Broadcom ones, VC4, V3D for the Raspberry Pis, and Nuvo has some embedded applications too. So really, I think nowadays we really support everything that's currently shipping. And thanks through all these infrastructure and helpers and user space, kind of same way we had in the kernel, you can write a really competent driver even if you have to reverse engineer the hardware. And the absolute massive demonstration of that is the RADV Vulkan driver, which is for AMD, not written by AMD, because the AMD driver is essentially, here's our proprietary project, but as part of the release script, we slap an open source license on it. So if you actually want to change something like real open source, real free software, it's useless. And RADV is developed by like distros, customers, people who want the real driver that they can change. And just last year, they started with a new compiler based on the NIR stuff and their own backend. And it is now actually beating AMD's driver across the board. And it's about 1 to 2 handful of people who do this as a part-time thing. And again, I have here a really great talk from the last conference. And the other thing that I want to call out specifically on the driver side and user space is, for a long time, Intel was really focused on the compiler side and figured everything else doesn't matter. It's not where the performance gains are. But then Vulkan happened and very clearly demonstrated that low overhead for draw calls and all these things hugely matters for performance. And about 2 years ago, we started this Iris project, which is a complete rewrite of the Intel OpenGL driver, using all the existing compiler infrastructure, all the libraries used for describing the hardware. And sharing buffering, the format layout information between Vulkan and the old GL driver. And there's two years ago, there was a talk by Kenneth Gronke about how in micro benchmarks, there's, I think, factor of 20 faster or something like that. And again, the benefit here is the shared infrastructure of this is using the Gallium framework for writing GL drivers, which everyone else has been using and optimizing for years. And so again, it's a really nice demonstration that once you have these kind of bits and pieces for reuse and figured out how they should look like, you can achieve really impressive drivers and performance metrics with, yeah, almost no people. And if you want to hear more, there's just after lunch, there's a talk from Robert Foss about Panfrost and how that reverse engineering story is happening. So if we kind of take these three things, like the buffer sharing, the display with Atomic, the compiler story, you think, well, you just write code, and after like about the 5th or 10th attempt at writing code, eventually you get it right and you win, and that's all. And I think that would be like hugely missing a story. So the other things that have been happening is all the known code stuff. Because of course, if you don't have code, you don't have a free software project, but code is not sufficient. So one thing we've done on the tooling side and related things is we've adapted Git before GitHub existed. That's largely just benefit to being closely aligned to the kernel. And I think this was a huge benefit. Unfortunately, we then slept for like 10 years. And finally, 1.5 years ago, we started adopting GitLab and modern processes and CI. Another thing we've done is we've adopted the code of conduct. I mean, the thing is, open source graphics is like 35 years old. And 35 years ago, no one was talking about having a code of conduct, or your community is kind of missing an important piece. And we got around to fixing that, which was kind of challenge because we adopted our code of conduct for graphics before the kernel had one. And so we had to adopt this in a somewhat hostile environment. We've cleaned up our governance structures, like there's the Xorg Foundation and the Free Desktop Project. They're now merged together. And I think the takeaway here is that if your project is going to survive for a few years, or has to, because, well, you need like 5 to 10 attempts until you get the code right. This is going to take some time. You need to adapt. Like there's things we're doing today that will look terrible to the people in 10 to 20 years. So I think another conclusion is you need to have some governance, like some way that you can make decisions and everyone is at least okay at the end with these decisions and these changes. And I think the big change here is you don't just need administration. You don't need just a bunch of people who keep the servers running and maybe, I don't know, conferences organized, but you really need something that has a way to make decisions. And if you go back more than 10 years in the free graphics community, Linux desktop, for the people who remember the X386 project and all the fun around that, we had a time where we did not have working governance and working structures, and it was really hurting us. So you have code, eventually you get it right, you have governance so you can adjust to the changing world and survive for long enough until you get the code right. But that's still not going to guarantee that you'll be able to stay around for long enough. The not so well-known fact of graphics is that just in the last 10 years, at least 3 companies tried to completely kill it and fire everyone. And the thing is, it's a big project. It's like there's, I think, like by now, hundreds of people working on this full time. You don't just write a graphics stack as a hobbyist while studying. You can do a lot of it like that. So essentially, you need to get your bills paid. And if you look at graphics, we have now multiple GPU vendors supporting this. We have Intel, we have AMD, we have the Raspberry Pi Foundations. We have a lot of the GPU vendors who at least support the kernel side. We have multiple OSs and distros and customers who pay people. So even if a company decides we're going to rage quit this and fire everyone, it's not going to kill kind of the overall project. We have multiple consulting shops. So if a customer has to deal with a vendor that just rage quit open source graphics because they don't like this freedom for the customer anymore, they can just make a call and have a good set of companies with competent people who can fix their problems. We don't have CLAs, so no company, no single entity has like control over this and can take it down. Our governance structure is not a company kind of pay-for-play structure, which means, again, like a company that turns evil, and sooner or later they're all going to do that. That's just how it is. Can take over and kind of destroy the project. And I think there's been lots of examples over the last 10 years of this happening to free software projects. And so fundamentally, like it's free software. It's about giving users more control and making sure there's no proprietary modes. And I think we've really succeeded at that in the graphics community. So another conclusion is, I would say, you need to have a business case and you need to have multiple because one of them is going to disappear. And if you don't have multiple business cases, multiple entities supporting your community, long term, I would say you're just not going to survive for long enough that you can rewrite your stack 5 times until you get it right. And I do think one of the key reasons why we do have this business case, that people do actually find free graphics drivers valuable, is this entire free software is about giving users control. But in graphics, we have this dual stack thingy. So fairly often, the hardware vendor is really not interested in giving users more control because they would like to get their users and customers to just pay more. It gets them more money. So you have lots and lots of graphics stack that maybe the kernel driver is open source or maybe some of the integration glue is open source, but most definitely the compiler is not open source and maybe other things are not open source. And from the upstream point of view, we always had the very clear rule of this is not worth it, go away, we're never going to merge it. And we pissed off a lot of people who said, but wouldn't this have been easier for like people if they could just install the NVIDIA driver or the Qualcomm driver or the ARM driver, because at least. And I do think, like just long term, this is killing the project. And if you don't have like that free software advantage, you don't really bring a benefit to the users. And long term, that means there's no one willing to pay for this additional work of reverse engineering GPUs. So we'll be, on the other hand, I mean, we also kind of want to make the companies feel welcome because obviously it's better if the hardware vendor is writing the driver and you don't have to reverse engineer it. So we have this kind of dual stacks are okay. The open source free software stack is definitely the one that matters, the one that's officially supported, the one that we're going to listen to if you get bug reports. But we're also okay if people take like the kernel driver in upstream and then run their proprietary user space on top of it, just to kind of help keep paying the bills until we've achieved the end goal of having a fully open stack. So the third thing, kind of takeaway, is have some principles. Like in the end, it's about free software. And personally, I feel like just selling out, even if it would be more convenient, even if maybe more hardware would work in the short term, long term, you're throwing out the benefit, you're throwing out the long-term business case that will pay the bills, and you will never be able to write like the 5th version of a GL compiler that finally is good enough that you can fully compete with all the closed source drivers with a handful of people. And if you want to hear more of this, especially like further back than just the 10 years, Keith Packard is doing a talk about the history of X and lessons learned for software freedom tomorrow, I think right after lunch. So that's where we're currently standing. Great stuff about the future, or maybe not so great stuff about the future. In the compute space, using GPUs to do all kinds of other things that have nothing to do with graphics, we have this problem that NVIDIA defines the standard with their CUDA APIs. That's not an open standard. It's just whatever NVIDIA is doing. And that obviously puts us at a massive disadvantage for getting anything in there. The other thing that's happening are these so-called TPUs, TensorFlow processing units for neural networks. And unfortunately, the people doing that somehow believe that a massive compute unit with a bunch of fixed functions slapped on top is not a GPU, despite that GPUs have essentially been massive processing units with a bunch of fixed functions slapped on top of it for 20 years. And that all the lessons we've learned here for free graphics drivers do not apply to TPUs. And they went ahead and merged kernel drivers for closed source user space. So I'm not super optimistic about what's going on there. The other thing is still like NVIDIA. They do not really seem to want to have users the freedom to do whatever the user wants to do, and prefer the user to do what NVIDIA wants them to do. Maybe this is changing, maybe it's not changing, because really NVIDIA is the only GPU vendor across the board, from servers to desktop to embedded. You cannot get a fully competent, fully supported open graphics stack from at least someone. A bit more on the positive side, Kronos, the standards body for OpenGL and Vulkan is massively opening up. We had the Kronos president attend our conference last autumn, and he's super enthusiastic about all the stuff we're doing. They have an open source test suite nowadays. Since a few years, they're really trying to open up the development process and flow for standards. Obviously, there's a bit a pull between kind of the closed source hardware vendors want to develop new standards and not talk about it until they're ready to do so, versus kind of the open source idea. But yeah, we have officially sanctioned and conformant implementations approved by Kronos, so this is working really well. On the compute side, I would say the thing today is attend Dave Early's talk about TensorFlow and open source GPUs at the end of this week, where he's going to talk about what all needs to be done and what has all been done already. So, summarizing, we have some really awesome tech. I talked about 3 examples. One is that atomic Modesetting. The second one was all the stuff we've implemented for cross-driver buffer sharing, getting agreement on the actual pixel and byte layout of the buffers, making sure that the different drivers coordinate their rendering. And the third one is the NER compiler. And I guess the conclusion there is I mean, atomic mode setting is roughly the 5th major revision of display drivers. If you look at user space mode setting, FBDEF, legacy, the old kernel mode setting from 10 years ago, and then Google with Android implemented the Android display framework as a first attempt at atomic, which wasn't really. It did solve their problem. It didn't solve any other problems. The cross-driver buffer sharing, I mean, if you looked at the list, we were at number 5 of how do we do synchronization, and we know that we need number 6 in a few years latest. The NER compiler is probably about major iteration number 5 in an attempt at doing a competent open source GPU shader compiler. So awesome technology, 5th time's a charm, 3rd time's probably not good enough. But the bigger lesson learned, in my opinion, really is, the code, eventually you will get it right as long as you have enough time. Meanwhile, and this was a tough one for me personally, merging bad code is actually good code because at least it gets you moving for another few years, where you can figure out what you really need to do. I mean, the thing is, we would never have developed Atomic 10 years ago or 15 years ago without all the lessons learned from all the other attempts, and same with the buffer sharing, same with the compiler and everything else. But really, to be able to iterate on the code and finally get there, you need to be able to survive for long enough, which means you need to be able to adapt. So you need to have some governance. You need to make sure that some company going down does not kill you. And finally, you need to have some principles to make sure that you survive for long enough. So thanks a lot.
Thank you very much, Daniel. We have run out of time for this one, but if you want to catch him later, we've got a lunch break coming up and everything else. On behalf of Linux Conference, we'd like to present you with this little memento from your speech.
Thanks a lot.
Thank you very much.